Assalamu alaikum. Let's start lecture number 30 of CS317 Operating Systems. The topic of this lecture is networking and distributed processing. We are using chapter 16 of the William Stallings book on operating system. In the last lecture, we discussed examples of service-oriented architecture and analyzed them. We were introduced to distributed message passing. We understood the different variations of message passing primitives. We discussed the remote procedure call mechanism on both client and server side. We talked about parameter representation and passing. We discussed different types of client-server bindings. We explored synchronous and asynchronous remote procedure calls. We were introduced to object-oriented middleware, and now we pick it up from where we left. The subtopic that we are going to talk about today is clusters. Let us first look at the definition. Clustering is an alternative to symmetric multiprocessing as an approach to providing high performance and high availability, and is particularly attractive for server applications. We can define a cluster as a group of interconnected whole computers working together as a unified computing resource that can create the illusion of being one machine. The term whole computer means a system that can run on its own, apart from the cluster. In the literature, each computer in a cluster is typically referred to as a node. Let us remind ourselves what symmetric multiprocessors are. A symmetric multiprocessor can be defined as a standalone computer system with the following characteristics. There are two or more similar processors of comparable capability. These processors share the same main memory and I/O facilities and are interconnected by a bus or other internal connection scheme such that memory access time is approximately the same for each processor. All processors share access to I/O devices either through the same channels or through different channels that provide paths to the same device. All processors can perform the same functions, hence the term symmetric. The system is controlled by an integrated operating system that provides interaction between processors and their processes. Any processor in the system can execute the operating system. Kernel modules can be run simultaneously on more than one processors. So there are a few points that we need to note. SMPs are shared memory architecture and clusters are distributed memory architecture. Processors in an SMP are on the same motherboard, but clusters have whole computers connected to each other, each computer with its own motherboard, RAM, and processor. An SMP system is run by a single operating system. Each computer in a cluster has its own operating system. The operating system on a cluster node recognizes that it is part of a cluster and enables the node to productively participate in the cluster. Now let us focus on the benefits of clustering. Absolute scalability. It is possible to create large clusters that far surpass the power of even the largest standalone machines. A cluster can have dozens or even hundreds of machines. each of which is a multiprocessor. People have developed clusters which have the same power as a supercomputer. Incremental scalability. A cluster is configured in such a way that it is possible to add new systems to the cluster in small increments. Thus, a user can start out with a modest system and expand it as needs grow without having to go through a major upgrade in which an existing small system is replaced with a larger system. High availability. Because each node in a cluster is a standalone computer, the failure of one node does not mean loss of service. In many products, fault tolerance is handled automatically in software. Superior price or performance. By using commodity building blocks, it is possible to put together a cluster with equal or greater computing power than a single large machine at much lower cost. If you look at the architecture of supercomputers, their RAMs, their motherboards, and their processors are fabricated for them. It is a special fabrication for a special machine, so obviously that fabrication is costly. But when you look at compatible clusters, clusters are built by off-the-shelf components, and those components have nominal prices. So there is a lot of difference in price of a cluster and the price of a supercomputer when both of them are yielding the same performance. What do you mean by availability of a system? Or what is an available system or a highly available system? Cluster architecture. Consider a two-node cluster in which interconnection is by means of a high-speed link for message exchange. The link can be a LAN that is shared with other computers that are not part of the cluster, or the link can be a dedicated interconnection facility. If the link is a dedicated interconnection facility, one or more of the computers in the cluster will have a link to a LAN or WAN so that there is a connection between the server cluster and remote client systems, not shown here. Basis of cluster classification. In the literature, clusters are classified in several different ways. The simplest classification is based on whether the computers in a cluster share access to the same disks. Using this criterion, we realize two classes of clusters: clusters with no shared disks and clusters with shared disks. No shared disks. It is easy to understand that this cluster does not have a shared disk. Note that each computer is depicted as being a multiprocessor. This is not necessary but does enhance both performance and availability. Shared disks. The other alternative is a shared disk cluster. There is a disk subsystem directly linked to multiple computers within the cluster. The common disk subsystem is a RAID system. If you remember, I asked you to read about the RAID when we were talking of IO management. The use of RAID is common in clusters so that the high availability achieved by the presence of multiple computers is not compromised by a shared disk that is a single point of failure. Classification based on function. A white paper from Hewlett-Packard provides these classes of clusters along functional lines: passive standby, active secondary, separate servers, servers connected to disks, servers share disk. And now we will look at them separately. Passive standby. A common older method of implementation is known as passive standby. One computer handles all the processing load, while the other computer remains inactive, standing by to take over in the event of failure of the primary. To coordinate the machines, the active or primary system periodically sends a heartbeat message to the standby. If these messages stop arriving, the standby assumes that the primary server has failed and starts operation. This approach improves availability but not performance. If the only information exchanged between the two systems is a heartbeat message, and if they do not share disks, then the standby can take over the primary's operations, but it has no access to the databases managed by the primary. Active secondary. The passive standby is generally not referred to as a cluster. The term cluster is reserved for multiple interconnected computers that are all actively doing processing while maintaining the image of a single system to the outside world. The term active secondary is often used in referring to this configuration. Three classifications of active secondary clustering can be identified: separate servers, shared nothing, and shared disk. Let us look at the separate server. Each computer is a separate server with its own disks, and there are no disks shared between systems. This arrangement provides high performance as well as high availability. Some type of management or scheduling software is needed to assign incoming client requests to servers so that the load is balanced and high utilization is achieved. This scheduling software accepts jobs from the clients, and then it looks at the current load of each server. Then it assigns the job to the server which is lightly loaded. And in this way, load balancing is done. It is desirable to have a failover capability, which means that if a computer fails while executing an application, another computer in the cluster can pick up and complete the application. For this to happen, data must constantly be copied among systems so that each system has access to the current data of the other systems. This data exchange ensures high availability at the cost of performance because there is a lot of data transfer on the high-speed message link. Shared nothing. To reduce the communications overhead, most clusters now consist of servers connected to common disks. In one variation of this approach, called shared nothing, The common disks are partitioned into volumes, and each volume is owned by a single computer. If a computer fails, the cluster must be reconfigured so that another computer gets ownership of the volumes of the failed computer. Shared disk. It is also possible to have multiple computers share the same disks at the same time. This is called the shared disk approach, where each computer has access to all the volumes on all the disks. This approach requires the use of some type of locking facility to ensure that data can only be accessed by one computer at a time. Operating system design issues that are relevant to clusters. Full exploitation of a cluster hardware configuration requires some enhancements to a single system operating system. We need to concentrate in the following areas: failure management, what will happen when a computer fails; load balancing, how will we distribute incoming jobs to the different servers in a cluster; parallelizing computation, what is work that can be done in parallel and how will it be done in parallel. Let's first talk about failure management. Two approaches can be taken to dealing with failures: highly available clusters and fault tolerant clusters. Highly available clusters. A highly available cluster offers a high probability that all resources will be in service. If a failure occurs, such as a node goes down or a disk volume is lost, then the queries in progress are lost. Any lost query, if retried, will be serviced by a different computer in the cluster. However, the cluster operating system makes no guarantee about the state of partially executed transactions. This would need to be handled at the application level. Fault tolerant clusters. A fault tolerant cluster ensures that all resources are always available. This is achieved by using redundant shared disks and mechanisms for rolling back uncommitted transactions and committing completed transactions. The function of switching an application and data resources over from a failed system to an alternative system in the cluster is referred to as failover. The restoration of applications and data resources to the original system once it has been fixed is referred to as failback. Failback can be automated, but this is desirable only if the problem is truly fixed and unlikely to recur. If not, automatic failback can cause resources to bounce back and forth between computers, resulting in performance and recovery problems. Suppose that a system fails. So you do a failover. You take the applications that were running on this system and move them to an alternate system. Then the system decides that the system which failed has recovered. So you do a fail back. You take the applications from the alternate system and put them back on the recovered system. Suppose that the problem has not been fully resolved. What will you have now? You will have a failure again in this system. Then you will again do a failover and then you will do a failback. So what will happen is that the application will keep bouncing from the failed system to the alternate system, back to the failed system, back to the alternate system. This will use up a lot of resources of the cluster, and it will slow down the cluster. It will create a very bad effect on the performance of the cluster. So this should not happen. Load balancing. A cluster requires an effective capability for balancing the load among available computers. This requires that the cluster be incrementally scalable. The cluster should be such that you can add nodes into it from time to time. When a new computer is added to the cluster, the load balancing facility should automatically include this computer in scheduling applications. Middleware mechanisms need to recognize that services can appear on different members of the cluster and may migrate from one member to another. This migration may be because the system was load balancing, so it migrated a service from a heavily loaded node to a lightly loaded node, and this migration may be because the original node failed, so the service was migrated to an alternate node. Parallelizing computation. In some cases, effective use of a cluster requires executing software from a single application in parallel. There are three general approaches to the problem: parallelizing compiler, parallelized application, and parametric computing. Parallelizing compiler. A parallelizing compiler determines at compile time which parts of an application can be executed in parallel. So what the compiler does is compiler makes a pass in the code and identifies the functions or modules of the code that can run independently and which have no data dependency. Remember, data dependencies occur when the output of one function becomes the input to another function. So if the compiler can identify functions which are not data dependent upon each other, then those functions can be executed in parallel. These are then split off to be assigned to different computers in the cluster. Performance depends on the nature of the problem and how well the compiler is designed. Some problems are inherently parallel. They can be broken into many different pieces, and those pieces don't have any data dependency. Some problems have no parallelism or very small amount of parallelism. Then the other thing is that the compiler should be really intelligent to identify that between these two functions dependencies do not exist, and between these two functions dependencies exist. So performance also depends upon the design of the compiler. Parallelized application. In this approach, the programmer writes the application from the outset to run on a cluster and uses message passing to move data as required between cluster nodes. This places a high burden on the programmer, but may be the best approach for exploiting clusters for some applications. When we conduct parallel processing practicals for our students, in those practicals we do cluster programming and we write programs using the message passing interface, which is an API. So when I am writing a program for a cluster, I think about all the things that I have to do. Then I think about what things among all of these things can be parallelized, and then I use specific MPI functions to parallelize those things. So here the crux of parallelization is upon me, and who am I? I am the programmer. So this is a way of writing applications which are written as parallel programs. Parametric computing. This approach can be used if the essence of the application is an algorithm or program that must be executed many times, each time with a different set of starting conditions or parameters. A good example is a simulation model, which will run many different scenarios and then develop statistical summaries of the results. For this approach to be effective, parametric modeling tools are needed to organize, run, and manage the jobs in an orderly manner. So your task is name at least two parametric modeling tools. Do that and then meet me again in the video. Cluster computing architecture. The individual computers are connected by some high-speed LAN or switch hardware. Each computer can operate independently. A middleware layer of software is installed in each computer to enable cluster operation. The cluster middleware provides a unified system image to the user, known as single system image. The user of a cluster does not know that the entity it is talking to is not one computer. He always feels that it is one computer. The middleware may also be responsible for providing high availability by means of load balancing and responding to failures in individual components. Desirable cluster middleware services. The first service is single entry point. A user logs on to the cluster rather than to an individual computer. Consider that the Google search engine is a cluster. When we write www.google.com, we log into this cluster, which then searches for our query. Does it ever occur to us that this is a cluster and not just one computer? No. Single file hierarchy. The user sees a single hierarchy of file directories under the same root directory. There are three computers in a cluster. Each has a C drive. In computer 1, inside drive C, there is a subdirectory named Uruj. In computer 2, inside drive C, there is a subdirectory named Ali. In computer 3, inside drive C, there is a subdirectory named Hina. But the cluster shows its users a single C drive that contains three subdirectories, Uruj, Ali, and Hina. This is a unified file tree. Single control point. There is a default node used for cluster management and control. This was previously called a master node, but now it is called the primary node. Single virtual networking. Any node can access any other point in the cluster, even though the actual cluster configuration may consist of multiple interconnected networks. There is a single virtual network operation. Again, there are three computers in the cluster. Computer 1 is connected to computer 2 with a cable, and it is connected to computer 3 with another cable. Even when computer 2 and 3 are not physically connected to each other, a process on computer 2 can access a service on computer 3 due to the virtual network between them. Single memory space. Distributed shared memory enables programs to share variables. The RAM card on each computer is obviously accessible to the processors that are on the same motherboard. But one processor on a computer can message a processor in another computer to share variable values from its RAM card. The primary memory is, although distributed among machines, it is still shared in the cluster. That is why we call it distributed shared. Single job management system. Under a cluster job scheduler, a user can submit a job without specifying the host computer to execute the job. Based on the requirements of the job, the scheduler can choose to send it to a specific computer or break it and make a set of computers work on it. Single user interface. A common graphic interface supports all users, regardless of the workstation from which they enter the cluster. Single I/O space. Any node can remotely access any I/O peripheral or disk device without knowledge of its physical location. Again, there are three computers in our cluster. Computer 1 is connected to a printer. This is the cluster's shared printer. So any node in the cluster can spool its files to this printer without worrying about if it is directly connected to the printer. Single process space. A uniform process identification scheme is used. A process on any node can create or communicate with any other process on a remote node. The process IDs used in the system are unique across the system. Sometimes the IDs are hierarchical, with their most significant digits identifying the computer hosting the process and the remaining digits identifying the process itself. Checkpointing. This function periodically saves the process state and intermediate computing results to allow rollback recovery after a failure. Process migration. This function enables load balancing. If we have a lightly loaded machine, processes from a heavily loaded machine can be migrated to this machine. Points to note. The last four items enhance the availability of the cluster. These are single I/O space, that is, any node can access any peripheral or I/O device, regardless of its location. Single process space. Every process can be uniquely identified across the cluster. Checkpointing. The process's state is saved and you can roll back to a previous checkpoint. Process migration. A process can be taken from its host machine and made to run on another machine in the cluster. The remaining items are concerned with providing a single system image. A cluster will also include software tools for enabling the efficient execution of programs that are capable of parallel execution. Have you ever used checkpoints before? If yes, where? Comparison of clusters with SMPs. Both clusters and symmetric multiprocessors provide a configuration with multiple processors to support high demand applications. Both solutions are commercially available, although SMP has been around far longer. An SMP is easier to manage and configure than a cluster. The SMP is much closer to the original single processor model for which nearly all applications are written. The principal change required in going from a uniprocessor to an SMP is to the scheduler function, as we now have more processes to distribute the processes over. The SMP usually takes up less physical space and draws less power than a comparable cluster. SMP products are well established and stable. Over the long run, the advantages of the cluster approach will result in clusters dominating the high performance server market. Clusters are far superior to SMPs in terms of incremental and absolute scalability. Clusters are also superior in terms of availability because all components of the system can readily be made highly redundant. So the lessons we learned today are: we explored cluster architecture, we explored classes of clusters, we outlined operating systems design issues regarding clusters, we listed desirable cluster middleware services, and we conducted a comparative analysis of clusters and SMPs. Things that you need to do are the same. You need to read the book and find answers to the tasks that I've set you. Note your questions and email your suggestions to me. However, this is the last time that I'm saying this to you because this is the last lecture in the series of lectures for the theoretical part of operating systems. So why don't we take a look at what we have done so far and how far we have come. We started with Introduction to Operating Systems, in which I gave you an overview of the history of computers. And then we came to processes and found what processes were. Then we did uniprocessor scheduling. Then we progressed to threads. Then we did a long chapter on concurrency in which we talked about synchronization and mutual exclusion. Then we went back to IO management, which was followed by file management. Then we revisited synchronization with the chapter of deadlocks. And then we came to networking and distributed processing. During this journey, I tried to make things as easy for you as I can. But I know that these were difficult circumstances, and all of us are actually just trying to cope with this pandemic. So I know that you people also have put in a lot of efforts in understanding this course, and there must have been shortcomings on my side, and I am sorry for them. I apologize. I must say that you have been a very nice class and you have taken interest in the content that I showed you, and your questions were slick and well timed, and I was really very delighted to answer them. It's time to say goodbye, class. I don't know if I will get a chance to have another semester with you, but I just want you to know that the time that we spent together in this online semester understanding operating systems was a very nice, delightful time. And I need to thank you for it. I leave you with these thoughts. Anyone who stops learning is old, whether at 20 or 80. Anyone who keeps learning stays young. That's how I stay young. The essence of teaching is to make learning contagious, to have one idea spark another. If I have made you yearn to learn, I have done what I was supposed to do. Thank you for a wonderful semester. Allah Hafiz.